What if we are not alone? The question lingers, a cosmic echo bouncing through the vastness of space and time. It's a question that has driven exploration, fueled imagination, and sparked countless dreams. This question has echoed through the ages, whispered under a canopy of stars by stargazers and philosophers alike. From ancient astronomers charting the heavens to modern scientists probing the depths of space, the quest to understand our place in the universe has been a constant companion. The search for extraterrestrial life is more than just a scientific endeavor. It's a deeply human quest, born from our innate curiosity, our profound desire to connect with something larger than ourselves, and to understand our origins. It speaks to our fundamental need to know if we are unique or part of a larger cosmic family. Imagine the silence of the cosmos, not as an emptiness, but as a language we have yet to understand. A language filled with subtle signals, complex patterns, and perhaps even voices waiting to be heard. It's a language we are only beginning to decipher. With every new telescope launched and every probe sent into the abyss, we gather more clues, patiently piecing together the puzzle of the universe, peering deeper into the unknown, hoping to catch a glimpse of something extraordinary. We are the first generation in human history with the technology, the resources, and the collective will to truly search for life beyond Earth in a meaningful and comprehensive way. We stand on the precipice of discovery. Now, with advanced spectroscopic techniques, we can analyze the atmospheres of distant planets, searching for telltale signs of life, like the presence of oxygen, methane, or other biosignatures. And with rovers exploring the Martian surface, we can drill into the rusty soil, analyzing samples for organic molecules and other potential signs of past or present biology. The search is on, and the stakes could not be higher. The discovery of life beyond Earth would fundamentally alter our understanding of the universe and our place within it. Let's explore the possibilities. From the hidden oceans beneath the icy surfaces of moons like Europa and Enceladus, to the tantalizing prospect of Earth-like exoplanets orbiting distant stars, residing within the habitable zone, where liquid water could exist. The journey begins here, with a deeper understanding of the delicate balance of conditions that allowed life to flourish on our own planet, a pale blue dot in the vast cosmic ocean. What if we are not alone, and never were? What if the universe is teeming with life, waiting to be discovered, waiting to connect? The cosmos waits for an answer, and humanity stands ready to listen. The greatest adventure of all time is about to begin. To find life elsewhere in the vast cosmos, we must first deeply understand why it thrives so abundantly here on Earth. What makes our planet so special, so uniquely suited to harbor the incredible diversity of life we see all around us? It's a question that has driven scientific inquiry for centuries, pushing us to explore the very limits of our knowledge. Earth's habitability isn't a given. It's a delicate and intricate balance of several key ingredients, working in harmony. At the forefront of these is liquid water, a protective atmosphere, acting as a shield against the harshness of space, and a stable temperature, maintained within a range that allows for liquid water to exist and for complex chemical reactions to occur. Water is far more than just a simple liquid. It's the universal solvent, the lifeblood of our planet, absolutely essential for the complex chemistry that underpins all known forms of life. It facilitates the transport of nutrients, the removal of waste, and countless other vital processes. Our atmosphere doesn't just provide us with breathable air. It also shields us from harmful solar radiation, preventing it from stripping away our precious water and ensuring that it remains in its liquid state. Earth orbits the Sun at just the right distance, within what we call the Goldilocks zone, allowing water to persist in its liquid form on the surface. This Goldilocks zone represents that sweet spot where temperatures are neither too hot nor too cold, but just right for liquid water. Too close to the Sun and we'd be scorched and barren like Venus, with runaway greenhouse effect turning our planet into an uninhabitable hellscape. Too far away and we'd freeze into a desolate icy wasteland like Mars, where water is locked away as ice and life as we know it would be impossible. These factors aren't isolated. They are deeply interconnected, creating a complex and dynamic feedback loop that sustains life and maintains the delicate balance of our planet. The oceans, for example, play a crucial role in influencing the atmosphere, absorbing heat and releasing water vapor, which in turn regulates global temperature, distributing heat around the planet, and ultimately keeping water liquid across vast regions. It's this intricate dance of geology, chemistry, and physics this symphony of interconnected systems that makes Earth a haven, a sanctuary for life to flourish. Therefore, when we embark on the ambitious quest to search for life elsewhere in the universe, we're not just looking for any planet. We're really searching for worlds that have, against all odds, struck this same delicate balance, possessing the essential ingredients for life as we know it. The recipe for a habitable world is undoubtedly rare, requiring a confluence of factors that may seem almost improbable, but it's not necessarily unique. The burning question remains: could other worlds, orbiting distant stars, have also stumbled upon this life-sustaining recipe? Could they too harbor the potential for life? Mars, our closest planetary neighbor, presents itself today as a cold, dry world. A seemingly desolate landscape stretches across its rusty surface, a stark contrast to our vibrant blue planet. The thin atmosphere and lack of liquid water on the surface make it a challenging environment for life as we know it. But remarkably, it wasn't always so. The Mars we see now is just one chapter in a much longer and more complex story. Evidence suggests a past where liquid water flowed freely, carving out landscapes that hint at a warmer, wetter world. Geological evidence, meticulously gathered by rovers and orbiters, reveals ancient riverbeds, winding paths etched into the Martian surface by long-vanished streams. These aren't just small trickles, they are substantial channels that once carried significant volumes of water. Deltas, the fan-shaped deposits of sediment formed where rivers meet a larger body of water, are also present. These formations are key indicators of past water activity, showcasing where rivers once emptied into lakes or even a vast Martian ocean. And lakebeds, vast expanses of sedimentary rock, tell a story of standing water that persisted for extended periods. These ancient lakes could have provided stable environments for the development of early life. All this serves as undeniable proof that water, the lifeblood of Earth, once flowed across the surface of Mars, shaping its landscape and potentially fostering conditions suitable for life. The question now is, for how long? Billions of years ago, during its early history, Mars likely had a significantly thicker atmosphere, trapping more heat from the sun and resulting in warmer temperatures. This warmer, wetter environment is crucial to understanding the planet's potential for habitability. Rovers like Curiosity, with their sophisticated instruments, have been instrumental in analyzing Martian rocks and soil, providing valuable insights into the planet's past climate and geology. And Perseverance, currently exploring Jezero Crater, a former lakebed, has found rocks clearly shaped by water erosion, further solidifying the evidence for a watery past and collecting samples for potential return to Earth. These rovers are meticulously searching for chemical fossils of ancient life, telltale signs that might indicate the presence of past organisms. They analyze the composition of rocks, looking for specific molecules and structures that could only have been formed by living things. The ultimate question remains: did life ever begin there? Did the conditions on early Mars allow for the emergence and evolution of microbial life? The similarities between early Mars and Earth are striking. Both planets likely had liquid water, thicker atmospheres, and similar chemical compositions, raising the intriguing possibility of a shared biological heritage. Could life have originated on one planet and then spread to the other? Life could have arisen independently on both planets, or perhaps even more fascinating, it could have traveled between them on meteorites, rocky debris ejected from one planet by asteroid impacts, and eventually landing on the other. Now, the search intensely focuses on biosignatures, complex organic molecules or microscopic structures preserved within Martian rock, acting as potential fingerprints of past life. We meticulously sift through the red dust, analyzing every grain, searching for echoes of a lost biosphere, a hidden world teeming with microscopic life that may have once thrived on Mars. Finding even a single fossilized microbe, a preserved remnant of a Martian organism, would be a monumental discovery, proving that life is not unique to Earth and revolutionizing our understanding of the universe. Mars, with its secrets locked within its ancient rocks, may yet reveal the astonishing truth that we are not alone in the vast expanse of the cosmos. The search continues, driven by our innate curiosity and the profound implications of such a discovery. The search for life extends beyond planets to the icy moons of Jupiter and Saturn, Europa and Enceladus. Beneath their frozen shells lie vast oceans kept liquid by tidal heating from their parent planet's gravity. These hidden oceans may contain more water than all of Earth's combined. Hydrothermal vents on their sea floors could provide energy, just as they do for life in Earth's deep oceans. On Earth, such vents teem with life, thriving without sunlight. The Cassini spacecraft discovered plumes erupting from Enceladus containing water, salts, and organic molecules. These geysers offer direct samples from the subsurface ocean. Europa and Enceladus may have all the ingredients for life: water, energy, and nutrients. If life can exist in Earth's extremes, why not here? These moons are among our most promising targets in the search for life. For most of history, we knew only the planets of our solar system, but in the last few decades, we've discovered thousands of exoplanets orbiting distant stars. The Kepler Space Telescope revealed a galaxy teeming with worlds, gas giants, super-Earths, and Earth-sized planets. Systems like TRAPPIST-1 host multiple rocky planets, some in the habitable zone. Even our nearest neighbor, Proxima Centauri, has a potentially habitable planet. This revolution has transformed the search for life from a local quest to a galactic one. Each new exoplanet is another chance for life to emerge. With trillions of planets, it seems unlikely Earth is the only one to host life. The odds are in favor of company. How do we narrow the search for life among trillions of planets? Scientists focus on the habitable zone, the region around a star where liquid water could exist. The size and location of this zone depend on the star's type. Planets must also be rocky and massive enough to hold an atmosphere. The star's stability matters too. Many red dwarfs are volatile, threatening habitability. The search is for a Goldilocks planet around a Goldilocks star. It's a cosmic trifecta. But with so many worlds, such planets likely exist. The shoreline of possibility is vast. Finding a planet in the habitable zone is just the beginning. The next step is searching for biosignatures, chemical clues in a planet's atmosphere that hint at life. Light passing through an atmosphere leaves a chemical fingerprint, detectable by powerful telescopes. Oxygen and methane together could signal a living biosphere. The James Webb Space Telescope can analyze exoplanet atmospheres for these gases. It's a painstaking process, but it lets us chemically probe worlds light years away. We also listen for signals. SETI scans the skies for patterns that could indicate intelligence. So far the universe is silent, but our search has only just begun. Each new discovery brings us closer to an answer. The cosmos may yet whisper back. Would we even recognize alien life if we found it? Our search is shaped by Earth's biology. We look for carbon-based life and water, but the universe may surprise us. Could life be silicon-based or use methane as a solvent like on Titan? Alien biospheres might produce unfamiliar gases, or none at all. Life could exist as a planet-spanning network or a sentient ocean. Our methods are biased by our own experience. The first sign of life may be a subtle anomaly, not a clear signal. To find life, we must open our minds to the truly alien. We stand at a unique moment in history, peering into a cosmos filled with trillions of worlds. The ingredients for life, water, organics, energy, are common throughout the galaxy. We've explored Mars, icy moons, and distant exoplanets, making the question of life more urgent than ever. Finding even simple life elsewhere would reshape our perspective forever. It would show that biology is a fundamental property of the universe. And if we find intelligent life, it would end our cosmic isolation and open a new chapter for humanity. For now, the universe is silent, but possibility abounds. Perhaps, on a distant world, another species is asking the same question. Are we alone? The search is a testament to our hope and curiosity. One day we may find what we're looking for. Until then, the cosmos waits.